Hi everyone, I'm Julia, the chemistry tutor, and today I'm going to talk about net ionic equations. Okay, so net ionic equations tell us about everything that was actually involved in a chemical reaction that occurred. So you've been balancing equations, putting everything in there, all of the stuff that goes in, all of the stuff that goes out. But not everything is actually involved in a chemical reaction. Some of them are just spectators. Some of the chemicals just watch what happens and are not actually involved in the chemical reaction. So that's what we're going to talk about today, is how to do a net ionic equation to show only the ions and chemicals that were actually involved in the equation. Okay, so when we think about net ionic equations, think about what the term net means. So like your net pay is your take-home pay. That is after the taxes are taken out. Okay, so your net pay is after taxes are taken out. A net ionic equation, we call them NIEs, is after spectator ions are taken out. Okay, so it's what we get after we take out the things not involved. So spectator ions are not involved in the reaction. Okay, they just show up, they spectate, they watch everything happen, and then they just leave. Okay, they just sit around watching things happen. They don't really leave, they're still there. They just sit around watching things happen. Okay, so when we're going to do a net ionic equation, our first step is to do a balanced equation. Okay, so remember from my balanced equation videos, we first need to know what our products are. And that is based on our type of reaction. We need to make sure that our formulas are correct. Because remember, if our formulas are not correct, our balancing will not be correct. Okay, so that's all based on our nomenclature. And then after our formulas are correct, we balance the atoms on both sides of the arrow. Okay, and our fourth step is we put in our states, and that is based on our solubility rules. Okay, so our first thing is to do a complete balanced equation, doing those four steps. Okay, so then for a net ionic equation, okay, we then split all strong aqueous. Okay, because that means that they dissolved in water. And so that means they are now in their ionic form. Okay, they're ions now. And we only split the strong ones. So that means we do not split solids, liquids, gases, or weak aqueous. And we're going to look at a chart, or your instructor is going to give you the information to tell whether or not it's strong or weak. Okay, so we split them all. We identify our spectators. Okay, and then we write everything that are not the spectators. Okay, so this one up here is what they call the molecular equation. This one here, where we split all of our strong ones and identify the spectators, this is our total ionic equation, all of the ions involved. And then when we write what's left, that is our net ionic equation. Everything that's left after we take the spectators out. Okay, so we're going to do some practice with those. Okay, so I am not going to spend a lot of time working on how I get the formulas for these. If you're curious about that, go back and watch my videos on nomenclature to figure out how I get my formulas. I'm not going to talk heavily about types of reactions. I'll mention them, but I'm not going to go deeply into types of reactions. Okay, if you want to know about that, go back and look at my types of reactions video. Okay, so in the interest of making this video not extremely long, I'm not going to go into detail on all of that because I've gone into detail on previous videos. Okay, so we have this first reaction here. We have ammonium phosphate. So I have ammonium and phosphate. Ammonium's +1, phosphate -3, 3 ammoniums. Reacts with zinc nitrate. Zinc is a +2, nitrate's a -1. Okay, this is a double replacement reaction. So they're going to switch partners. My ammonium hooks up with my nitrate and my zinc. Give myself a little space there. My zinc hooks up with my phosphate. Okay, so I have my balanced equation. Okay, so now that we're going to look at the states. Okay, and if you recall from our solubility rules, all group 1 and ammoniums, the ammonium ion, are always, always, always soluble, always aqueous, no matter what. Our nitrates and our acetates are always soluble, no matter what. So we don't need to look those up, okay? So we have an ammonium here. We know that that is aqueous. We have a nitrate. We know that that is aqueous. We have an ammonium and a nitrate. We know that that is aqueous. So we'll have to look up that zinc phosphate. Okay, so I will pop over to our solubility rules. And we're looking at zinc phosphate. So zinc is not rule number 1. So we go to our phosphates. And phosphate salts are typically insoluble except with rule number 1. Okay, so zinc is not rule number 1, which means that that is insoluble. It is a solid. So that zinc phosphate is a solid. Okay, so on our rules, we balance our equation. So we haven't balanced that equation yet. I put in my states before I balanced. I'm going to start with zinc phosphate on balancing. So I have 3 zincs and 2 phosphates. So now looking here at ammonium nitrate, I have 6 ammoniums and 6 nitrates on the other side. If you struggle with the balancing of that, go back and watch my balancing equations video. Okay, so now we balance, then we split all strong aqueous. Okay, so we know we're not going to split that because that is a solid. Okay. Let me pop back over to those electrolyte table. Okay, on this table up here, this is how I tell if they're strong or weak. Okay, is this up here, this top part, and your instructors might give you this type of table. They might give you something else, but they'll give you something so you know whether things are strong or weak. Okay, and I'm going to draw a line down the middle here. Okay, so here's your strong electrolytes are in the left-hand column. Okay, you only have 6 strong acids. Remember, acids have hydrogens in the front. So you only have 6 strong acids. If it's not one of those 6, it is weak, and we don't split those. And if it's a solid, So you might or might not have solid acids in this class. Okay, we don't split those either. We only split for acids. We only split those 6 strong acids. Okay, for our bases, bases have OH in the back, the hydroxide. Okay, we have these strong bases. This is our only weak base, and you will, I don't know about your instructor, if they call it weak as a reactant only or as a product. You'll need to ask your instructor about that. But even though ammonium hydroxide is soluble because it's got the ammonium ion, it's actually weak. We would not split it in a net ionic equation. And then for salts, salts are ionic compounds. Okay, so if it's got a metal and a non-metal, it is a salt. And basically all aqueous salts are strong. Some of your instructors may have some weak ones. If you have weak ones, you just don't split those. And these would be solids. And you know you don't split those anyway because we only split strong. Okay, these are weak over here for our bases. We don't split those. And we don't split those because these are solids. Okay, so you only split what is in your left-hand column over here. Those 6 acids, those bases, and aqueous ionic compounds. Okay, I wrote a few things up here to save me from having to pop back and forth between those screens all the time. So I wrote down what our strong acids are up here. Those 6 strong acids are strong bases, that all aqueous salts are strong. That's how I'm doing it. If your teacher says differently, you will have some weak ones that you do not split. I wrote that these are always soluble. We don't need to look at our solubility rules for those. And here's our steps for net ionic equation. That's how we do a net ionic equation, is those steps. Okay, so on this, we already did a balanced equation. Now we're going to split all of our strong aqueous. So that first one is an aqueous salt. So if I have 2 of those ammonium phosphates, I have 6 ammoniums. So we split them out all into their individual ions. Put your charge with your ion and put your state. They stay aqueous. Okay, if I have 2 of these, I have 2 phosphates with his charge and aqueous, because they are now just floating in solution. Okay, they've split apart into their ions and they're just floating in solution. So my zinc nitrate, I have 3 zincs with his charge and state. I have 6 nitrates. On the other side, another aqueous salt, I have 6 ammoniums. And if I have 6 ammonium nitrates, I also have 6 nitrates. And I'm out of space, so I'm going to write this down below. I have that this is a solid, so we are not going to split that. So I have a zinc phosphate. Okay, that is my total ionic equation. This one up here was my molecular, just a balanced equation. Okay, so now I'm going to identify my spectators. Spectators are the same exactly on both sides of the equation. I did not explain that earlier. A spectator ion is exactly the same in the reactants as it is in the products. Same charge, same number of them, same state. Okay, so when I look here, my ammonium, those are spectators, because they're exactly the same on both sides. 6 of them with a positive charge and aqueous. Our 6 nitrates are the same, exactly the same on both sides. So those are my spectators. My ammoniums and my nitrates are my spectators. Okay, so now my last step. So we did our balance. We balanced the equation. We split all of our strong ones. We identified our spectators. Now we're going to write the non-spectators. So I have 2 phosphates. with 3 zinc ions, making a zinc phosphate. Okay, and that final equation needs to balance also. We have 3 zincs on both sides, 2 phosphates on both sides. Okay, so that is my net ionic equation. After I've taken out my spectators, it's like all of these over here on the reactant side, they all showed up to the dance alone, but then zinc and phosphate hooked up and left the dance together. Ammonium and nitrate just watched the action happen. They just spectated. They were not involved in that reaction. Okay, so let's do our next one. We have lithium hydroxide. Lithium's a +1, hydroxide's a -1. Reacts with manganese sulfate. Manganese, our name told us, was a +3, sulfate's a -2. So 2 manganese and 3 sulfates. That is, again, a double replacement reaction because I have an ionic compound with an ionic compound. They're going to switch partners. Lithium hooks up with the sulfate, and manganese hooks up with the hydroxide. Okay, so looking at our charges, I'm a +1 and a -2. So I need 2 lithiums on my lithium sulfate. My manganese hydroxide, I need 3 hydroxides. And again, if you struggle with that, either email me to set up a private session at juliachemtutor@outlook.com. Okay, you can set up a private session with me and I can help you out with that, or go look at some of my other videos on balancing equations and nomenclature. Okay, so I got my products based on my type of reaction, double replacement. I made sure my formulas were true based on my nomenclature. Now I'm going to balance those atoms on both sides. I'm starting with manganese sulfate. I feel like he's got the most stuff in him. Okay, so I've got 2 manganeses on the reactants. I'll put a 2 on the products. I have 3 sulfates on the reactants. I'll put 3 on the products. And I have 1 lithium on the reactants and 6 on the products. So I'll put a 6 on the reactants. And I have 6 hydroxides on the reactants and 6 hydroxides on the products. Okay, so we're balanced. Now we're going to do the states. Okay, so the one thing we know is that group 1 metals are always, always, always soluble no matter what. Okay, so lithium being a group 1 metal, always aqueous, and he's also aqueous on that side. Okay, the manganese sulfate and manganese hydroxide, we don't have any absolutes for those. So I'm going to pop over to the electrolyte table. And we're down here to decide whether or not we're soluble. So I have manganese hydroxide and manganese phosphate. Oh, is that right? Nope, I have manganese sulfate, I think. Okay, so my sulfates here. Okay, sulfates are usually soluble except with, and manganese is not an exception. So manganese sulfate is soluble, it's aqueous. Here's my hydroxides. They are typically insoluble except with rule number 1, calcium, strontium, and barium. So manganese is not an exception, meaning that it is insoluble. That is a solid. Okay, so we go back to our other sheet. My manganese sulfate was soluble, aqueous, and my manganese hydroxide was a solid, insoluble. Okay, so we balanced our equation. We got all of our solubilities in there. Now we're going to split all of our strong aqueous. Okay, so remember, any salt, so my bases, bases, hydroxides in the back. Here's my bases up here. Okay, lithium hydroxide is a strong base, so we're going to split that. We also know because it's a group 1 metal, group 1 metals are always strong. Okay, so 6 lithium ions and 6 hydroxide ions. Okay, my manganese sulfate is a salt. Any aqueous salt is strong. So I have 2 manganese ions and 3 of those sulfate ions. Okay, over on the other side, lithium. Okay, I've got an aqueous salt, so it's strong. So again, I have 6 lithium ions. I have 3 sulfate ions. And manganese hydroxide is a solid. We are not going to split it. We're just going to leave it exactly like it is. Okay, so now we identify our spectators, things that are exactly the same on both sides of the equation. So I have 6 lithium ions, 6 lithium ions. I have 3 sulfate ions and 3 sulfate ions. And that is all because my hydroxide and manganeses are not exactly the same on the other side. So I write down my 6 hydroxide ions, my 2 manganese ions, makes my 2 manganese hydroxide compounds. Okay, and those need to balance on both sides. I have 6 hydroxides on both sides and 2 manganese on both sides. Okay, so that's my net ionic equation. The one above it was my total ionic equation, and then this one was the molecular. That was a double replacement reaction. Okay, so now on my next one, magnesium metal. So I have magnesium, and mercury is your only liquid metal. It is the only metal that is not a solid. So we already know magnesium is a solid. We don't need to look anything up about that. Okay, it reacts with hydrochloric acid. Remember, your hydro acids have no oxygens. So it's just the chloride. He's a 1 negative, so 1 hydrogen. Okay, I don't know if you noticed, but I have a single thing here and a double thing here. That is a single replacement reaction. Okay, my magnesium would be a cation. Hydrogen is the cation. So magnesium kicks the hydrogen out and takes the chlorine. Okay, so magnesium hooks up with the chloride, kicks the hydrogen out. Okay, so we got our products based on our type of reaction. We need to make sure our formulas are true. Magnesium is a +2 and chloride's a -1, so I need 2 chlorides. And we know hydrogen is one of our diatomics, so I need a 2 on him. Okay. All right, so I got my products based on my type of reaction, made sure my formulas are true. Now I'm going to balance them. Okay, I see that I have 2 hydrogens and 2 chlorides on the products. So I'm going to put a 2 in front of my hydrochloric acid, and we are balanced. Okay, so now to do the states, I did not write this up here, but all acids, as far as most instructors go for allied health chemistry and general chemistry, all acids are aqueous. Okay, not all acids are strong. We only have 6 strong acids, but they are all aqueous. If they're not in water, if they don't get put into water, they're actually a gas. Okay, so we know that that hydrochloric acid is aqueous because all acids are. We know hydrogen is a gas. Remember when we did the solubility rules, I said gases and liquids you kind of need to know off the top of your head. Okay, and then that magnesium chloride, if we go to our electrolytes, we are looking at chlorides. Chlorides are right here. Okay, they are generally soluble with, and magnesium is not an exception, so it is soluble. That is aqueous. So magnesium chloride is aqueous. Okay, so we got our states in, so we have the full balanced equation now. Now we need to split all of our strong aqueous. Magnesium is not aqueous, so we just leave it like it is. Hydrochloric acid, we go up here to our acids, and we see hydrochloric acid is one of our strong acids, so we are going to split it. If I have two of them, I get 2 hydrogen ions and 2 chloride ions. Over on the other side, we said all aqueous salts are strong. Magnesium chloride is a salt ionic compound, so I get a magnesium ion and 2 chloride ions. And then that hydrogen is a gas. We just leave it like it is because we only split strong aqueous. Okay, so now I identify my spectators. Okay, so following our rules up here. Okay, I did my balanced equation. I split all of my strong. Now I'm going to identify my spectators. Things that are exactly the same on both sides. My magnesium is not the same. This one is a solid with no charge. This one is aqueous with a charge. Those do not cross out. Those are not spectators. He changed. Okay, my 2 chlorides did not change. They are exactly the same. So now my last step is to write what's left. So my magnesium reacts with 2 hydrogen ions, and you get a magnesium ion and hydrogen gas. There is my net ionic equation. Okay, molecular up top, total ionic in the middle, net ionic at the end. Okay. Oh, you know what I did not do with that? That is a single replacement reaction. We have to look at the activity series to see if that reaction will actually happen. Remember when we did types of reactions on single replacement reactions, we have to make sure that that magnesium is stronger than the hydrogen in order to kick him out. Okay, so let's go look at that real quick. So, really? Okay, well, you see on this chart magnesium and hydrogen. So magnesium is 1, 2, 3, 4, 5, 6, 7, 8 down, and hydrogen's near the bottom. Magnesium is definitely stronger than hydrogen. He will definitely kick him out. Reaction will happen. The next one that I have in there, since I have this open, is copper reacting with silver nitrate. So we're looking to see if copper is stronger than silver. And right underneath hydrogen is copper. And then 2 below him is silver. So copper is above silver. Copper is definitely stronger than silver. The reaction will happen. Okay, and I was looking at that because this next one is copper with silver nitrate. Okay, so again, I have a single, let's go ahead and write our formulas. So copper metal, I have copper. He's a metal, so he's a solid. Reacts with silver nitrate, so silver and nitrate. Silver is a +1, nitrate's a -2. So if I swap those, I need, nitrate's a -1. Sorry about that. Okay, so they already equal 0. That formula is good. So a single replacement reaction. So we already said copper was stronger than silver. So copper being the cation will kick out the cation. Okay, so copper kicks out silver and hooks up with nitrate. I don't know if you recall from my types of reactions videos, but if we have a variable charge metal, On these single replacement reactions over here, we assume it's a +2 and copper is a -1, so I need 2 nitrates on there. Okay. All right, so my formulas are correct. Now I'm going to balance those atoms. I'm going to start with the copper nitrate. I have 1 copper on each side. I have 2 nitrates on my products, so I'll put a 2 on the reactants, give me 2 nitrates. That gave me 2 silvers, so I'll put a 2 on my silver on the products to give myself 2 silvers. Okay, so now I am balanced. Now I'm going to put my states in. We already said a metal sitting there by itself is a solid, so copper is a solid. If we look at our absolutes up here, nitrates are soluble no matter what. Okay, so both of those nitrates are aqueous. And silver metal is a solid. Okay, so now I have my entire total balanced equation with the states in there. Now I'm going to split all of my strong aqueous. Solids are solids, they're not going to split. My aqueous, any aqueous salt is strong, so I get 2 silver ions, 2 nitrate ions. Over on the other side, copper nitrate is an aqueous salt, so it's strong. So I get a copper +2. We had said that in a single replacement reaction, variable charge metals, you assume a +2. I have 2 nitrates on there. And I get 2 silver solids. Okay. So I balance my equation. I split my strong aqueous. I did not split my solids. And now I identify my spectators. Copper is not the same on both sides. This one is a solid. That one is aqueous with a charge. Silver is not the same on both sides. This one on the reactants is aqueous with a charge. This one on the products is a solid. Not the same. They do not cross out, not spectators. They were involved in the reaction. My 2 nitrates are exactly the same on both sides. Okay, so my copper metal reacts with my 2 silver ions to produce a copper ion and 2 silver metals. Okay, so there's our net ionic equation. And the reason I wanted to make sure I did that one is so you see that they are not the same. When one is a solid and one is aqueous with a charge, they are not spectators. They do not cross out. Okay, and I did not list my spectators here. Okay, if they asked you to list them on this one up here, you would list that your ammonium and your nitrate are both spectators. Those are the ones that we crossed out there. On this one, my lithium, I don't have much room there. My lithium and my sulfates are the spectators. On this one, my chlorides were the spectators, because the chlorides were what I crossed out. And then on this one, my nitrates were the spectators. Okay, so let's do another one. So I have sodium phosphite. So sodium phosphite. And I'm not even going to do the charges anymore. I'm just going to write the formulas just to save us some time. Okay, so potassium sulfite. That is, again, a double replacement reaction because I have an ionic compound with an ionic compound. Sodium hooks up with sulfite, and potassium hooks up with phosphite. Okay, and I'm not going to spend a lot of time balancing this. Okay, so I'm now balanced. Okay, so now I'm going to put my states in. I Okay, again, if you struggle with that, go back and watch my balance and equations video or email me for an appointment. Okay, so all of these are group 1 metals. Potassium and sodium, both group 1 metals. Okay, and we said all group 1 metals, no matter what, up here are soluble always. Group 1 metals are always soluble, always strong aqueous. Okay. So all of these are aqueous because they all have a group 1 metal as the cation. Okay, which means they are all strong aqueous salts. So they are all going to split. So I get 6 sodium ions, and that is 2 phosphite ions. I get 6 potassium ions and 3 sulfite ions. Okay, see where I got all those from? I have 6 sodiums, 2 phosphates, 6 potassiums, 3 sulfites. Over on this side, I have 6 sodium ions and 3 sulfite ions. I have 6 potassium ions and 2 phosphite ions. Okay, so I split all of my strong aqueous. Everything was strong. And here's the deal. When everything is a strong aqueous, they are all spectators. My 6 sodiums on both sides are exactly the same. My 2 phosphites are exactly the same. My 6 potassiums, exactly the same. My 3 sulfites, exactly the same. So this is considered a no reaction. Nothing actually happened. Nothing reacted. They all showed up to the dance alone, and they all left the dance alone. Nobody hooked up at the dance. Nobody got a date at the dance. Okay, so if they all cross out, if they're always group 1 metals, if everything in there is a group 1 metal, it is always going to be a no reaction. They are always going to cross out. You still have to do the process, but your end result will be a no reaction. Your net ionic equation is no reaction. Okay, so now I've got sulfuric acid with barium hydroxide. Okay. Again, that is a double replacement reaction, but it's the special one, the acid plus the base, the neutralization. So your barium hooks up with the sulfate, and your H hooks up with the OH to make water. But remember, it's easier to balance it if we see it as HOH. Okay, and my formulas are correct, and I have 2 hydrogens and 2 OHs, so I'll put a 2 in front of my water. Okay, so that is balanced. And we had said all acids are aqueous no matter what. I'll have to look at that base. I'll have to look at the barium sulfate, and water is a liquid. Okay, remember, liquid is pure. Water is like your one pure liquid. There's nothing dissolved in it. An aqueous solution is something dissolved into water. It is no longer pure water. Okay, so we're going to look at that barium sulfate and barium hydroxide real quick. Okay, so if I'm looking at my barium sulfate, okay, so here's our sulfates here. Okay, so they're generally soluble, except, barium is an exception, which means that that is a solid. Okay, so barium sulfate is a solid, insoluble. And then we have hydroxides. So our hydroxides here, and those are typically insoluble except for, and barium is an exception. So barium hydroxide is aqueous. Okay, so our barium hydroxide, we said, is soluble, and our barium sulfate is not soluble. It is a solid. Okay, so now I have my equation is balanced. I have my states in there. So I'm going to split all of my strong aqueous. Okay, so the acid and the base, remember we have to go look at our table. Okay, I wrote my table up here to make it easy on ourselves. So our acid is the sulfuric acid. And you'll notice here it says only the first hydrogen. We don't take both of those hydrogens from sulfuric acid, only one of them. Okay, and the base was barium hydroxide, and barium hydroxide is a strong base. So we're going to split both our acid and our base. Okay, and on that sulfuric, when it says first hydrogen only, you only take one hydrogen off and you leave behind the hydrogen sulfate ion. Okay, my barium hydroxide is strong, so my barium ion, and I get 2 hydroxide ions from that. Over here on my products, I have a solid and a liquid. Neither one of them are going to split because we only split strong aqueous. So those come down exactly like they are. Okay. So now if we identify our spectators, nothing is a spectator. There's absolutely nothing that is exactly the same on both sides. Nothing crosses out. So you just write that it is the same as the total ionic equation. You generally don't have to rewrite the whole thing. You just write that, okay, my net ionic equation is the same as my total ionic equation. Okay? All right, so now I've got strontium hydroxide with nitric acid. So strontium hydroxide with nitric acid. Again, acid plus a base, it's a neutralization, which is a double replacement. Strontium hooks up with nitrate, and H hooks up with OH. Okay. And to balance that, I'll start with my strontium nitrate. I have 1 strontium on each side, 2 nitrates on products, 1 on the reactants. So I'll put a 2 on my nitric acid. That gave me 2 hydrogens. So I'll put a 2 on my water and 2 hydroxides. I'm good, I'm balanced. Okay, so we have a balanced equation. Now we need to put in our states. Okay, so acids we know are aqueous, so I'll go ahead and put that one in there. Water we know is a liquid. Nitrates are one of our absolutes. Nitrates up here, soluble no matter what. They are no exceptions to that. They're always soluble. So that strontium nitrate is aqueous. But we need to look at the strontium hydroxide. Okay. So if I go back over to my other sheet, I go to my hydroxides. Okay, we're right here at the hydroxides again. Generally insoluble, usually they're solids, except for strontium is an exception. So that is aqueous. Exceptions are aqueous. So strontium hydroxide is aqueous. Okay, so we have total balanced equation with our states. So now we're going to split all strong. Remember, acids and bases, you have to look to see if they are strong. And I'm going to go back over to that other sheet just to show you that I already wrote all of these down up here. So our acids, we had nitric acid, and he is one of our strong acids. And we had strontium hydroxide, and he is one of our strong bases. Okay, so the nitric acid and strontium hydroxide are both strong. So we're going to split both of those. So I get a strontium ion, 2 hydroxide ions. Split my nitric acid because he's strong, 2 hydrogen ions, 2 nitrate ions. Over on the other side, I have an aqueous salt. All aqueous salts are strong. So strontium ion, 2 nitrate ions, and water is a liquid, so we just leave it like it is. So when I go to identify my spectators, strontium is the same on both sides. Hydroxide is not, hydrogen is not, but my 2 nitrates are. So if I write what's left, I have 2 OHs plus 2 H's, making 2 waters. Now, some instructors are picky about this and some are not. Balanced equations are supposed to be in the lowest possible ratio. So since those are all 2, we would typically get rid of those 2's in front. Okay, and this is a reaction we call water formation. Okay, and a lot of times that's just your reaction. The H's and OH's hook up together to make water. Okay. Okay, these last 3 are actually going to be really quick, and they're just going to prove a point, the final point I want to close with today. Okay, so we have potassium chlorate decomposes. So potassium chlorate, okay, decomposes. Remember, decompositions require heat. And if you recall, decompositions are done on solids. Okay, and they always produce solids and gases. Okay, so if I balance that, I get that. Okay, what you'll notice is there is no aqueous. There's nothing aqueous in a decomposition reactions. So you will not do, there's no net ionic equations with decomposition reactions because decomposition reactions don't involve any aqueous solutions. There's nothing to split. Okay, so now I have here is a combination reaction. Hydrogen combines with oxygen. And what could that possibly do except to combine together to make water? Okay, hydrogen is a gas, oxygen is a gas, and water is a liquid. Again, I have absolutely no aqueous in there. Even if I did a different combination, if I did magnesium plus oxygen to make magnesium oxide. Here, I'll go ahead and balance that just because. Okay, there's no aqueous. There's nothing aqueous in there. Even if I did have an aqueous that maybe I had, no, it just wouldn't happen. Okay, so there is no net ionic equations with combination reactions either. Okay, and then down here we have a combustion reaction. Okay, and I'll tell you that's a liquid. I did not tell you in there. We know combustion requires oxygen gas, always produces carbon dioxide gas and water gas because that is heated. Okay, again, it's all liquids and gases. There's nothing aqueous in there. Absolutely nothing to cross out. So you will also not do net ionic equations with combustion reactions. Okay, so you'll notice what I did up here was single replacement and double replacement. This one was a double replacement neutralization. This one was a double replacement neutralization. Double replacement. This one was a single replacement. Single replacement, double replacement, double replacement. Okay, so we only do net ionic equations with single replacement reactions and double replacement reactions. Okay, and they're fairly easy to do. Our biggest thing is, remember, we first need the balanced equation. Then we split only the strong aqueous, and we look at our electrolyte table or the list our instructor gives us to tell if they're strong or not. Identify your spectators and remove them, and write what's left after the spectator. So there's your net ionic equation. And I do believe that is all I have to say about net ionic equations today. So have a great day.